Hello friends, welcome to this webinar organized by Binary Semantics, Understanding General Relativity with Maple's Visualization. I'm your instructor, Professor Shyamkant Anwane. I'm associated with Sri Shivaji Education Amravati's Science College Nagpur, and I'm associated with Indian Association of Physics Teachers. Let's get involved into the basic fundamental equations of general theory of relativity, and then later on we'll explore the Maple worksheets with a very few commands, and we'll be effectively making wonderful calculations that months you will be required to cover, that you can do in Maple in fraction of second. Very quickly here, I would like to roll through certain things that one is learning in the junior college level physics, that is vector form of Newton's law. When we have two gravitating objects, they attract each other. The force of attraction is directly proportional to product of their masses, while it is inversely proportional to square of the distance between them, and the direction will depend when you are considering force on the second object due to first object. It will be g into m1 m2 upon r square, that is the distance between first and second object, into a unit vector r12 cap. R12 cap will be R12 bar upon magnitude R12, and R12 is R2 bar minus R1 bar. Here you can visualize R2 bar minus R1 bar. It will be along this direction. And when you take origin of the coordinate system at the center of the major gravitating object, say an earth, and you can consider this an apple, and in that situation force can be expressed like this, where this negative direction is associated with unit vector ar cap, which is borrowed from the spherical coordinate system, and the negative direction indicates that it is directed towards the center, whereas by definition ar cap is directed outwards. Then we already know the Newton's first law of motion, second law of motion, that force is equal to mass into acceleration, that is mass into acceleration due to gravity, and this acceleration due to gravity can be represented by g is equal to minus gm upon r square ar cap. Now here we are talking about the Newtonian approach, and then we are going to head towards general theory of relativity. The Gauss law regarding the gravitation problem. By Newtonian approach, we are going to discuss g bar from classical mechanics can be expressed as minus gradient of phi, which is in fact a gravitational potential function. And this gravitational potential function phi is equal to minus gm upon r. Here, I want to be very specific about a thing, that when we are talking about this phi, that is gravitational potential phi, this phi is function of r alone. It does not depend upon theta and phi. That offers it a specific symmetry, and then we want to perform divergence of g, that is del bar operator operated on g bar, where this g bar is to be replaced by minus gradient of phi. This offers us minus del square phi. This del square is called as Laplacian operator, and phi is the same gravitational potential function. Now, del square operator in spherical coordinates can be represented as the one appearing on your screen in the square bracket. and you very clearly know that phi is function of r alone. It does not depend upon theta and phi. So these derivatives d d theta of phi and will be 0, and its further derivative with respect to theta. So this whole term is going to vanish. Similarly, second order derivative of capital phi with respect to small phi, phi is function of r alone, so this will also be 0, and therefore we can further simplify this equation with the help of this m, what we call as mass. This mass m I'm going to write as in the form of density, where density we refer as mass upon volume. Volume is spherical volume is 4 by 3 pi r cube. So simplifying this equation, I want to write m as rho v, that is density multiplied by volume of the sphere, and when you simplify this you obtain 4 by g rho v. So here divergence of g, that is equal to 4 pi g rho or rho v, whatever you call. This is known as Gauss law. Now, as regards to tensors, when we look at these issues from mathematics point of view, people say that let us suppose that we have n-dimensional space or d-dimensional space. So there they are talking about n as any great number, d as any great number. But practically when physics people are dealing with the situation, they are talking about three-dimensional space. So 3D space means the dimension d is equal to 3. In general theory of relativity, we are going to use time as one of the dimensions, and then three dimensions of space, that is x, y, z. This makes four-dimensional case. So basically tensors are n-dimensional or d-dimensional in general. But here in this case, we are going to talk about the situation d is equal to 4 in case of general theory of relativity, and in simple geometry we talk about d is equal to 3. A scalar function phi of x, which depends on variable x, that x in d-dimensional space will have x superscript 1, x1, x2, x3 and xt. So where d is the dimension of the space. Now d phi can be written as a rate of change of phi with respect to the first variable x1 into the change that you are considering dx, so on and so forth for the number of dimensions involved, and you can represent the same thing in the compact form using this summation notation. And Einstein has given us summation convention. We need not write this. Whenever the index is repeating, it means that the summation is to be carried on that indices, that index. Now, for one-to-one correspondence from one coordinate system, say x, to another coordinate system y, where x is having d number of dimensions and y is also having d number of dimensions, expressed by variables x1, x2, x3 and so on xd, to y1, y2, y3 and so on up to yd, we represent del phi by del yn equal to del phi by del xm into del xm by del yn. So here yn is depending on x variable. There is a one-to-one correspondence, as we said. We can write this. Now here we have summation convention, and we can express this in this way. So we have introduced this dummy variable xm, and we are considering the transformation, you can say, from x coordinate system, capital X coordinate system, to capital Y coordinate system. This is governed by this tensor equation. Similarly, the change in phi, del phi by del y2, we can write introducing dummy variable xm. So on and so forth. We can go on making this, and we can write del phi by del yn equal to del phi by del xm into del xm by del yn. Here the dummy variable is xm. So m is a index that is repeating over, so you have to consider summation over that. So this is how tensor goes up. Now we have change in y. First variable dy1 is del y1 upon del xm dxm. So this is the kind of first tensor, and this is the kind of another second tensor, and we can write expressions for this. And this is how a generalized representation of tensor Vn that depends on variable y is equal to del yn upon del xm into Vm, which is function of x. Now these are two kinds. One is called contravariant, another is called covariant. So this kind of gradient representation, and when phi is replaced by yn and we differentiate with respect to ym, then we can write this in this fashion. So instead of phi we are using yn, and this is the kind of contravariant tensor, and this is a kind of covariant tensor. Well, we'll go ahead. Now the tensors of second order, when we have two vectors, basically I would like to define tensor is tensor of rank 0 we can call scalar, tensor of rank 1 we can call vector, and then we can have tensors of higher order. In general relativity, we'll be talking about tensor of second order, third order, fourth order, and the tensor of fourth order we are going to reduce to a scalar, that is called curvature scalar curvature we can call. So here we have two components m and n, and am bn, this product, which is product of tensor of rank 1 into tensor of rank 1, this offers us tensor of rank 2 in D square space, and that can be written as Tmn. So we can expand that Tmn in this way, the way we have defined, and here we have encountered with Trs, which is a kind of tensor related to Tmn, and the governing equations offering relation between two, they are as appearing on the screen. Now more explicit representation you can see on your screen. So a kind of very interesting quantity, that is metric tensor in general relativity. Consider a three-dimensional flat coordinate system which is governed by variables x, y, z, that is being represented by what you call x superscript 1, x1, x2, x3, and so on. The length element in this case ds can be represented by ds square can be represented by dx square plus dy square plus dz square. In general, it can be represented by dx1 square, dx2 square, and dx3 square. This can be written as dxm into dxm. Now, here we are using Kronecker delta symbol so that we want to avoid the unwanted factors here, and we can write del mn is equal to 1 when m is equal to n and other components 0. So that makes a metric tensor. So we can rewrite the metric tensors in the same fashion, where you can observe this GRS, which is actually del mn into del xm by del yr into del xn by del ys. Here GRS is called as metric tensor, which is actually collection of these partial differentiating objects. Now this is a very common example one has done sometime in a very early class, where we are talking about the polar coordinate system, and in polar coordinate system we have basic representation being made by what you call Cartesian x-axis, y-axis, and a point can be represented by traveling say x distance along x-axis and then y distance parallel to y-axis. And when we are interested in finding the distance between this point and origin, then it is obviously by Pythagoras theorem, it is x square plus y square in the under root. Now this quantity we call distance of the point from origin, and locus of all points which are at fixed distance from origin, that gives rise to a circle. But which point on the circle, that's a big question, and to identify that we specify the distance r, which is from center to that point, that makes an angle theta with x-axis. So this point, which was earlier represented by xy, can be represented by r, that is its distance from origin at an angle theta with respect to x-axis. So obviously here we have x is equal to r cos theta and y is equal to r sin theta. These are the transformation relations. Inverse transformation relations are r is equal to under root of x square plus y square, and theta is equal to tan inverse of y by x. We have already learned this sometime in the junior college, and when we want to make a generalized representation, instead of x I am writing x1, and instead of y I am writing x2. So r is being written by y1, and here also y1, and theta is being written by y2. This is not y square. So here I am using that transformation objects, and here you can identify ds square, which is equal to dx square plus dy square. This is equal to dr square plus r square d theta square, and this metric tensor object is this Kronecker delta times this partial differentiating objects, which gives rise to 1 0 0 r square. So here you can identify that the multiplying factor of dr square is 1, and multiplying factor of d theta square is r square. Other mixed components are 0, that is being represented here. So GRR is, I'll choose a color, GRR is equal to 1. GR theta and G theta R are 0, and G theta theta is R square that you can identify here. Now Cartesian to spherical coordinate system. Here I'm not very much interested in giving much time for this discussion. So here it is 1 r square and this is r square sine square theta. This object is called metric tensor, which is being represented by GRS, that is function of y. Y means second coordinate system, X means Cartesian coordinate system, so Y becomes spherical coordinate system here. Now interval in special theory of relativity, as I said, dA square is GMN, which is a metric tensor, multiplied by dxm dxn, and for special relativity this set is simply Kronecker delta, because c square dt square, actually c square dt square d tau square minus d lambda square. So we are considering two objects at same location in frame S dash, where we refer special relativity, and so we have only this interval equal to c square dt square minus dx square. So for four-dimensional space-time continuum, d tau square will be dt square minus dx square minus dy square minus dz square, and here we have introduced c equal to 1 without the loss of generality. We can recover c wheresoever we want, and for simplicity of equations we shall put c is equal to 1. We shall consider a unit system where the value of c is unity. So the coordinate set can be represented by x superscript mu, which is x0, x1, x2, x3, that has corresponding nature time, space, space, space. Sometime it can be t, r, theta, phi in spherical coordinates. So d tau square can be represented by eta mu nu, dx mu, dx nu, where eta mu nu is represented by this matrix, and the general uh, interval, general what you call metric tensor, can be represented by g mu nu having unity at the first diagonal element and minus of the function, which is function of time, that represents expanding universe. So when we are taking derivative of tensor, we have to be little careful that when we differentiate this Vm, which is actually the object composed of one partial derivative into this v of x r. So when you differentiate this, you have to apply chain rule, and that chain rule results into two terms where this object, which is mixed partial derivative, that is an added element that comes out of application of chain rule while differentiation, and we can write derivative, which is we shall not call this as normal derivative, we shall call this as covariant derivative. So del n, that is covariant differentiation of Vm, that is function of y, is partial differentiation of Vm with respect to yn plus this Christopher symbol gamma r m n, which is actually this quantity, mixed partial derivative, into Vrx. So sometimes some authors are writing this del Vn as this sign del n that is covariant derivative of Vm, which is depending on variable y, this kind of. Okay, so this is the Christopher symbol. Fine. So here I am operating covariant derivative of second rank tensor, wherein we have del p operated on Vm. So here this is Vm function of y. So you have to differentiate with respect to yp on Vm, and then this is Christopher symbol multiplied by Vr function of x. This in fact is a tensor. So derivative of tensor is also a tensor, one of the theorem in hardcore mathematics of tensors. Now, covariant differentiation of tensor of rank 2. So here n I have underlined for specific purpose of remembering this identity, and then you make simple derivative of Tmn with respect to yp, and then gamma rpm operated on rtn, gamma rpn multiplied by tmr. So this leads to a tensor of rank 3. Now, finding Christopher symbol is very important. There's one derivation which is appearing on your screen that can be used to obtain Christopher symbol, and in problems we are going to deal with, we have to obtain Christopher symbol for that given particular matrix, what you call the matrix element. So gamma ABC basically is equal to 1 by 2 GAD, where D is a dummy variable, and you have to sum over this D all the time when you consider the product. So I'm trying to underline this D. So here partial differentiation with respect to YB is represented in compact way here. Partial differentiation with respect to YC in compact way is represented here, and partial differentiation with respect to YD we are going to cover here with this comma D appearing here. So basically G is a metric tensor. G DC you can say B. This is partial differentiation with respect to YB of GDC. So while handling a problem, you will be able to understand how to find Christopher symbol for given metric tensor. Now, let us roll through the example that we have discussed for polar coordinates, and here actually we are supposed to find this Christopher symbol. Actually, r and theta are two coordinates. So here dimension d is equal to 2, and Christopher symbol has three variables like gamma, a, b, c. So 2 into 2 into 2 will lead to 8 kind of Christopher symbols, whereas 2 are identical. Gamma r r phi, instead of theta here I have used symbol phi, and gamma r phi r, they are identical because mixed partial derivatives are same. So by finding one you can obtain another. Sorry. And here phi, gamma phi, r phi, and gamma phi, phi r, this mixed partial derivative is identical. So instead of 8 we are leading to 6 only. 1, 2, 3, 4, 5, and 6. So let us pick first one for calculation. Gamma r, dummy variable is small gamma appearing here, and this is the differentiation sign with respect to r. Now let us do that calculation. Here gamma mu nu, we have seen this is a matrix 1 0 0 r square. So inverse of that is g superscript mu nu. It is appearing like this. So obviously g mu nu into g mu nu, this is equal to 1 because two matrices are inverse of each other. So here we are interested in finding gamma r r r. So the formula, here I have written this formula 1 by 2 partial derivative with respect to r of GRR. Now GRR is 1 and G theta theta is 1 by r square for this, and for this it is r square. You have to understand this. Now GRR is unity, as I said. GRR is 1. So this quantity is unity, and partial differentiation with respect to r of 1, this will be obviously 0. So the other quantities, this repeat of thing 0 plus 0, and GRR again 1 partially differentiated with respect to r. So independently all three are 0. So gamma r r is equal to 0. Likewise, many components are 0, only non-zero components are to be considered. So I am jumping on, so this quantity gamma r r phi is also 0. The non-zero component I would like to discuss. So here gamma r phi phi, this is equal to, by formula it is like this. On simplification, and it offers, it is minus 1 by 2 del r of g phi phi. So what is g phi phi? You have to understand, uh, 0 sorry 1 0 0 r square. So g phi phi is r square. So you can understand this is g r square, and then you have to partially differentiate that with respect to r. So this will be twice r multiplied by minus 1 by 2. So twice r multiplied by minus 1 by 2, it leads to minus r. So on and so forth, you can go on making calculations. In Maple worksheet, we are going to roll through these calculations. Now, the last component calculation is gamma r phi phi equal to minus r, and gamma phi r phi is 1 by r. So you can try it on your own. Now Christopher symbol for spherical coordinates I have calculated. You can pause the video and note down the gamma calculations, and you can verify that in the Maple worksheet it will appear as Christopher symbol of kind 2. Now covariant path derivative, that leads to a kind of equation which is shortest path between 2 points in the space-time continuum, and it is called geodesic. So here d phi by ds is equal to d phi by dy m into dym by ds. So this kind of chain rule, and d phi by ds will represent how the scalar field phi will change along the curved path s, and this is del ym, that represents a displacement vector, and this represents tangent. Obviously the rate of change of ym with respect to s will be tangent along the path. Del phi by del s, which is a scalar, Del phi by del s is a scalar which is product of two covariant, which is product of not two covariant, which is product of covariant part into contravariant part. This leads to scalar. The way g mu nu into g mu nu was leading to unity, the covariant and contravariant leads to a scalar. Now, the geodesic can be represented by this equation. The properties of geodesic, they are the straightest possible curves in the curvilinear coordinates of space and time, or you can say t, r, theta, phi in spherical coordinates. The covariant derivative of a tangent vector is always 0. Geodesic is a curve whose tangent vector is covariantly constant. The term covariant derivative does not mean that the object is covariant. Rather, we deal with the covariant derivative of contravariant component. So this is the equation of geodesic. And then Einstein's field equation I am going to put forth you. R mu nu minus 1 by 2 g mu nu into R is equal to kappa times T mu nu. So this whole quantity is called as g mu nu, and g mu nu plus capital lambda, which is the constant given by Einstein, cosmological constant, into g mu nu equal to kappa times T mu nu, and this is a Riemann tensor, which is a tensor of 4 order, 1, 2, 3 and 4, and it can be contracted further for the curvature scalar. Now the Schwarzschild metric is represented by 1 minus 2 gm upon r. Here in this equation all the way we are considering c equal to 1, so c is not appearing here, minus dr square upon the same bracket, it is appearing in the denominator, minus r square d omega, where d omega has meaning d theta square plus sine square theta d phi. Now here we are going to have the metric tensor g mu nu composed of a function which does not depend on time, it depends on the space coordinate r, and then minus v function of r, and these are the components of the metric tensor r square and r square sine square theta with minus sign. So I want to take you on the right in Maple worksheet now. Here all the way we are into the Maple worksheet that I have already developed. I have keyed in the instructions that I am going to now only roll through, only run, and here we are going to talk about the polar coordinates. Restart is a command to begin our programming. All accumulators are cleared with tensors and with differential geometry. Actually here I am not using differential geometry, but this file is also enabled, and coordinates we are talking about r and theta, and the components of the sparse matrix all are 0, basically 0 0 0 0, and now I am going to enter 1 1 and 2 2 component as 1 and r square respectively, and now you can see the matrix, and then I am going to run the command tensor gr, coordinates g, contravariant matrix, determinant, Christopher symbol C1 and C2, Riemann tensor, Ricci tensor, and then scalar curvature, then Einstein tensor, So we are asking to display the result. So the result is displayed. We shall scroll the output. So here you can see the components coordinate variables are r and theta. X1 and x2 is being replaced by r and theta, and the covariant matrix of having non-zero components as sorry, G11 and G22 respectively 1 and R square. Their determinant is R square. Their inverse, that is contravariant components are 1 and 1 by R square, and the corresponding Christopher symbol that we have calculated in the PowerPoint presentation, they are R and minus R. Christopher symbol of kind 2, actually these we have calculated, one of that we have calculated, other you can find it is 1 by R. So gamma 122 is minus R and gamma 212 is 1 by R. So this is a kind of flat situation where the Ricci scalar is 0, Einstein tensor is also 0 because there is no curvature, and Wiley tensor is also absent. Now we shall go for another file that is regarding spherical coordinates. Now for this I am going to run the worksheet that is already prepared. You can see only these commands I have entered. You can pause the video and take a screenshot to note down the commands that you can use independently. Restart with tensors, coordinates. Actually, I have written here spherical coordinates. It should be what you call cylindrical coordinates. So I'm correcting. So the coordinates are rho, phi, z, and the sparse matrix will appear like this. 1 row 1 will be the non-zero diagonal elements, and for this we can find out the Christopher symbol. Here you can see rho phi z, then you can see here the covariant components. Contravariant components are 1 upon rho 1. Then Christopher symbol of first kind will be plus 1 by 2 minus 1 by 2. Second kind it will be minus 1 by 2, and 1 by 2 rho. The Riemann tensor is only non-zero component is 1 upon 4 rho for R1212, and Ricci tensor like this. Ricci scalar for cylindrical curvature is like this, minus 1 upon 2 rho square, and Einstein tensor non-zero component is only G3, and Wiley tensor all components 0. Now we shall go for spherical coordinates. So for spherical coordinates you can see r theta phi. I am just running the commands, and the sparse matrix will be 1 non-zero diagonal element 1 r square sine square theta, and for this we are making the calculation of all parameters that include Christopher symbol of second kind. Here we have done this in the PowerPoint presentation, and this is how you can calculate the things. Now the next is the Schwarzschild solution. For Schwarzschild solution, I have picked up something from the book by Professor Frank Wang, and in the description link I'll give you the title of the book. So here the line element is like this, 18.36, and we can find the Christopher symbol using Maple. If you do it manually, it will take a lot of efforts, and the geodesic equation like this. So actually I want to show you the actual commands that we are going to use here, and the earlier part was a image of book. So with tensors is the first command we are using here, and the coordinates are spherical coordinates with time t, r, theta, phi, and g11, g22, g33, and g44 we are entering. You can see here in the matrix, and then tensor calculations for general relativity we are making, and we are asking for display of the same. So everything is displayed here. The last command I am running, that is geodesic equation, and then I'll scroll to show you the entire file. So here you can see the parameters that we have entered are t, r, theta, phi, covariant metric non-zero components that we have entered, which was for Schwarzschild solution. After covariant, we are having contravariant components, so that covariant into contravariant will lead to unit matrix. Christopher symbol of first kind you can see on your screen, non-zero component. Actually they should be 4 into 4 into 4, that is 4 into 4, 16 into 4 will be 64. Only non-zero components are listed here. This kind 2 Christopher symbols, and this is a Riemann tensor, and then Ricci tensor, non-zero components. Ricci scalar is 0 because we are talking for the flat space, and Wiley tensor is appearing like this. The geodesic equation you can see on your screen. Now after this I would like to show you a limiting case of general relativity that reduces to the Gauss law that we have derived in the beginning. So here these are the only set of commands that I have used, and I want to increase the size of font. So restart with tensors, coordinates t, x, y, z, sparse matrix. The elements are entered and you can see the matrix G. Then you can calculate tensor gr. You can run this command and then you can ask for display. So the display part is running, it is completed, and now you can see the display part. So here a big calculation is being presented here, where Christopher symbol of kind 2 you are observing on your screen now, only non-zero components. So Christopher symbol of kind 2. Prior to that there will be Christopher symbol of kind 1. I am ignoring that solution, and after that you can see the Riemann tensor, non-zero component R1212, then R1213, so on and so forth. Only non-zero components are being listed here. Then Ricci tensor. So the tensor of rank 4 is reduced to tensor of rank 2, and that is R11, R22, R23, R24, R33, R34, R44. Then Ricci scalar is being represented here, you can observe, and then Einstein tensor components G11, G22, so on and so forth. And I have considered only G11 part. So here G11 part I have picked up. Then T11 I'm substituting rho, that is mass density, and G11 and T11 I have picked up so that I can find the first element comparison in Einstein's field equation, and for limiting situation that leads us to Newtonian uh, mechanics, where C, that is upper limit, leads to infinity, and T11 is density. So here you can see the same equation, del square phi equal to 4 pi rho g. So here 2 is appearing on left hand side and 8 is appearing on right hand side. So you can divide the equation by 2 and we obtain Gauss law. This is a very interesting example people do while learning relativity. Now we are heading to the last, almost last file. I'm going to show you a couple of more files where we are going to uh, roll through the Schwarzschild solution, wherein we have the line element composed of the diagonal element, where the part is function of space as well as time. This is not a static solution. So Christopher symbol of kind 2, then Riemann tensor you can see on your screen, Ricci scalar you are observing on your screen, then Ricci, uh, then I'm going to run the command for Einstein tensor GE, and then Wiley tensor, and then geodesic equation, and Ricci tensor. So this is one part. Second part I want to show you where we are doing a kind of animation, and this image is from the Wang's book, where we are talking about geodesic equation, where we are uh, considering its variation, D'Alembert principle, for this line element ds square by 2 equal to 0, and this leads to Euler-Lagrangian function f, and this function I am using here. So from restart you can observe the commands that I am going to run, and now this file also I am going to run step by step so that you can observe on your screen what is happening. So I have picked up the function which is Euler-Lagrangian function, and then I'm going to substitute tau of t. Actually I want to see the output of this, so I am not suppressing the output now. So function in the blue color you can observe, this t is function of tau that I want to treat as a variable 1, and I'm changing over the variables, and then I'm making some substitutions, and then after substitutions I'm getting some equation, and again combining isolating equations I can obtain certain solution where I'm preferring mass equal to unity, gravitational constant equal to unity, and speed of light is also equal to 1, so that I can scale the uh, I mean geodesic path equation in a proper form, and I should be able to obtain the effective potential energy plot. Then you can see the animation of the path being tracked by the particle in space-time curvature, and the three-dimensional animation of the same thing you can observe here. So these many calculations are possible very easily using Maple. You can explore it on your own. Sorry, and on your own you can rebuild whatever you like, whatever changes you want to make, once you set up the changes, you'll be able to ascertain proper solution. But prior using Maple for general relativity, I believe that you should be able to understand that relativity theory. Then I wanted to show you something more that includes Robertson-Walker model. And in Robertson-Walker model, again, we are going to this file I'm running commands, and you can see the metric tensor I'm using for Robert-Walkerson model, where A of t is the uh, expansion factor which depends on time, and for this we are calculating the general relativity tensor, and then we can ask for a display of all quantities. I think it is taking trouble to run now. So yes, it has displayed the output. So here you can see this is a Christopher symbol of second kind for Robertson-Walker model. This is the Riemann tensor, Ricci tensor, Ricci scalar you can see on your screen. Then Einstein tensor non-zero component you can see. Now I'm running the command for geodesic equation. So that's appearing on your screen, and you can see the again the Einstein tensor, and this is the contravariant matrix of Einstein tensor, which is for Robertson-Walker model. Now this is one simple solution to Robert-Walkerson model, which we call evolution of universe, and here I found some trouble in running simple file actually, that is that ordinary differential equation is square of dA by dt equal to 1 upon A. A is function of time, and boundary condition we are taking A0 equal to 1, and we can solve this. So here the expansion A is proportional to t to the power 2 by 3 for some given boundary condition. Very quickly I want you to roll through a couple of things again which are not pertaining to what you call general theory of relativity. I want to show you a wonderful animation of quantum tunneling. Yes, it is here. So this is being picked from the support website of MapleSoft. So here you can control the barrier width. So here in the diagram you can very well see that you can change the barrier width. Then I'll ignore imaginary part. So here you can see probability, density, everything is absent. Okay, so initial potential V1 you can change, barrier potential V2 you can change, then V3 can also be varied. Energy of the particle which is tunneling, small energy, 1/3 energy of the barrier approximately. And now I want to introduce the real part so you can see the tunneling effect. If I change the barrier width, you can see how the transmission changes. Then in the same diagram I am introducing imaginary part, and then psi you can observe, probability density you can observe, and it can be animated over time. So if you change the width, the transmission probability reduces, you can observe. And as the energy of the particle increases, the transmission coefficient increases. So this is a wonderful animation that students can understand for swallowing the subject, I believe. So let us conclude here. I hope you might be having questions, but because of power failure, I could not interact with you. So I'm giving you this video through binary semantics. Thank you very much. This is the cover of the book that I have referred all through for this particular lecture. Thank you very much for your attention.